Hello everyone. So in my last lecture I had discussed about the pipelining of an IIR filter using the method look ahead transformation. So by applying m level of look ahead transformation, the filter was divided into FIR part and IIR part. So if this is my filter, yn is equal to E of yn minus 1 plus xn, and if I will apply m level of look ahead transformation, okay, so the filter will become like this. Now yn will be equal to E of m y of n minus capital M plus summation I equal to 0 to m minus 1 e raised to power I x raised to power n minus I. Okay, and this filter will be divided into two parts. First is a non-recursive part, that is FIR part, represented by this equation, and then IIR part, this equation, this term. So input is xn, output is yn. Okay, and considering this equation, so this equation is not having any FIR part, so number of adder and multiplier in FIR part is 0. It is just a IIR filter. Okay, so it has only one adder and one multiplier. Now talking about this part, the IIR part will remain same, one adder, one multiplier, but m number of delays. And talking about this part will have m minus 1 adder, m minus 1 multiplier. Okay, so you can see that there is a linear increase in the computational unit in the FIR part. Okay, from 0 for m level of transformation, m minus 1, so 0 to m minus 1 increase by m. So area of FIR part is linearly increasing because of this. So this was already mentioned in the last lecture. So hardware increase linearly with m. So the circuit with a large area is not attractive. Okay, so we have to find a way to decrease this area. Okay, and that can be done by the technique look ahead pipelining with power of 2 decomposition. Okay, and this will be used for implementing the non-recursive part, that is FIR part, and you will see that because of this the number of computational unit, that is adder and multiplier, will be increased by amount log 2 m. Okay, so first I will take an example and then things will be generalized according to the result. So again, starting with the same filter, yn is A of yn minus 1 plus xn. Okay, example, and let m is 8 level of look ahead transformation. So this equation will become yn, that is equal to a raised to power 8 y of n minus 8 plus summation I equal to 0 to 7 e of I x of n minus I, and that is equal to e raised to power 8 y of n minus 8 plus xn plus a times xn minus 1 e raised to power 7 x of n minus 7. Okay, and this can be implemented in a traditional way. So xn, first FIR part. Okay, so xn this is a delay element, so this is xn, this multiplied by a, added with xn, a times xn minus 1, then again a delay element multiplied by a square, and then added to the previous result, again a delay element multiplied by a cube, again a delay. Okay, so this is the block diagram representation of this equation, and here you can see that in the FIR part, this is the FIR part. Okay, so in FIR part, number of adders are 7, 1 2 3 4 5 6 7, and number of multipliers are also 7. And in IIR part, adders are 1, multipliers are 1, and number of delays increased by 8. Okay, so now this equation can also be represented in Z domain. So I can write in Z domain capital YZ will be equal to e raised to power 8 z raised to power minus 8 yz plus xz plus e z inverse xz plus e square z minus 2 xz till e raised to power 7 e raised to power z raised to power minus 7 xz. Okay, so yz by xz can be written as 1 plus ez inverse plus e square z minus 2 plus e cube z minus 3 plus e4 z minus 4 plus e5 z minus 5 plus e6 z minus 6 plus e7 z minus 7, and in the denominator 1 minus e raised to power 8 z raised to power minus 8. Okay, so now we have to evaluate its poles and zeros. So it has one pole at z equal to a. That was an original equation. This equation given by yz by hz 1 upon 1 minus az inverse. So it has pole at z equal to a, and this will also have a pole at z equal to e. Okay, and remaining 7 poles and zeros, they will be cancelling poles and zeros. So 7 cancelling poles and zeros, will be at position z a times e raised to power j 2 pi by 8 dot k, where k is equal to 1 2 3 up to 7. Okay, so I can represent them on a graph. So this is the real z axis, imaginary z axis. So in z plane I can draw them. So this is a pole at z equal to e. Okay, and the remaining 7 cancelling poles and 0 will be at this position. So like this. Okay, so 45 degree, 90, like this. So 1 2 3 4 5 6 7 cancelling poles and zeros, each separated by an angle of pi by 4, 45, 2 into 45, 3 into 45, 4 into 45, likewise. Okay, so now I have to decompose this. Okay, this FIR part is linearly increasing. Now I have to decompose it, and that too by the factor 2. Okay, so the level of transformation was 8. Okay, so now m divided by 2 gives me 4. 4 divided by 2 gives 2, and 2 divided by 2 gives 1. Okay, so for m equal to 8, if I will divide it by 2, I will get 1 at the last in 3 steps. Okay, so total 3 steps. And also log to 8 is 3. So if I start dividing m by 2, so I can divide it at most by these number of steps, log 2 of m. Okay, log 2 of m. So for m equal to 8, log 2 of 8, that is 3. Okay, so now the FIR part. Okay, so the FIR part will be decomposed into log 2 8, that is 3 stages. Okay, stage number 1, this is first stage, this is second stage, and this is third stage. Okay, so I am drawing it on next page. So this is FIR part. And the IIR part as it is. Okay, so now considering this stage, this is stage, instead of stage 1 I am starting my numbering from 0. So this is stage 0, stage 1, stage 2. Okay, so for this and this, we started decomposing 8. So 8 by 2 is 4, 4 by 2 is 2, 2 by 2 is 1. So 8 by 2 was 4, this is m by 2. For this, m divided by 2 divided by 2, and for this, m divided by 4 divided by 2. So this is 8 by 2, that is 4, 4 by 2, that is 2, and 2 by 2, that is 1. Okay, so the transfer function of this stage, as the decomposed value is 1, so the transfer function of this stage will have a degree of polynomial 1, like 1 plus e z minus 1. So the degree of the polynomial is of order of 1, that is minus 1. This stage, the value is 2, so it will have a transfer function of this kind, 1 plus e square z minus 2. So degree of the polynomial, highest degree will be 2, minus 2, and this part will be 1 plus e square z of minus 4, like this. So this into this into this, if you multiply this 3 terms, you will get 1 plus e z minus 1 plus e square z minus 2 up to e7 z minus 7. You can verify that. Okay, so now we have 3 different independent FIR filters connected in a cascade form. Okay, so this is stage 0, this is stage 1, this is stage 2. This filter, FIR filter, is having a transfer function of 1 plus Ez inverse, which is cascaded to this filter, which is having a transfer function of 1 plus a square z minus 2, which is again cascaded to the third filter, which is having a transfer function of 1 plus a square z of minus 4. Okay, so this is transfer function h z, and this is having transfer function of 1 upon 1 minus e raised to power 8 z raised to power minus 8. Okay, so finally the transfer function at z will be multiplication of all the transfer function, that like this, or you can also write it like I equal to 0 to 7 e raised to power I z raised to power minus I 1 minus e raised to power 8 z raised to power minus 8, like this. Okay, so you can verify by multiplying the 3 different polynomials, the result will be the same. So now talking about their so zeros of this FIR filter will have zeros. Okay, so this filter will have a 0 at, this is real z, this is imaginary z. So this stage 0 will have a 0 at z equal to minus a. Okay, this filter will have a 0 at z equal to a e raised to power. Okay, so this will have a 0 at z equal to minus a. You can easily evaluate that this part will have a 0 at z equal to a times e raised to power j pi by 2 and a into e j into 3 pi by 2 at this point on the imaginary axis. Okay, this is 0, sorry, this is 0. So this part will have 0 at location a into e raised to power j pi by 4, a into e raised to power j 3 pi by 4, a into e raised to power j 5 pi by 4, and a into e raised to power j 7 pi by 4. Okay, this is 5, and this can also be drawn very easily. So the location will be somewhat at this point. Okay, so comparing with this, the first part is having 0 at this location, the second part is having 0 at this location. Okay, the first part is having only 1 0, the second part is having 2 0, and the third part is having 4 zeros, 1 2 3 and 4, like this, 1 0 2 0 3 0. So number of zeros in this is 2 raised to power 0, 2 raised to power 1, 2 raised to power 2. So that's why I numbered this stage from 0 1 2. So stage 0 2 raised to power 0, stage 1 2 raised to power 1, and stage 2 2 raised to power 2, that is 4. Okay, so this is the pole and zero plot. Now I'm talking about its decomposed transfer function. So at z is equal to 1 plus e z minus 1, 1 plus e square z minus 2, and 1 plus e raised to power 4 z raised to minus 4, divided by 1 minus e raised to power 8 z raised to minus 8. Okay, so this is part 1. So xz given to multiplier multiplied by a and delayed by 1, z inverse, and then added to xz itself. So this is part 1, 1 plus az inverse. Similarly, the second part can be drawn. Okay, so this will be given to this will be, this is these, they are in cascade. So the output of this first part will serve as input to this second part. So this will be given to a multiplier, and the coefficient is now a square, and that will be divided by z of minus 2, and then finally we will add these two terms. This is second part. And this will serve as input to the third part. So we have again a multiplier with coefficient a raised to power 4 and delayed by z raised to power minus 4, and then adding two terms. Okay, and the IIR part will remain as it is, so I am not drawing this IIR part as it is. We will have yn, final yn. So this is part 3. Okay, so now you can observe that in each stage the number of multiplier is 1 and the number of adder is 1. Okay, in this stage number of multiplier is 1, adder is also 1, and in this stage also number of multiplier and adder are 1 1 each. So total adder is 3 and total multipliers is also 3. and that is again log 2 of 8. Okay, why this factor? Because we have divided the FIR part into this number of stages, and each stage is having one adder and one multiplier. Okay, so here you can see that the hardware is increased as a function of log 2 of m. Instead of linear increase, it is a logarithmic increase. So from 7 to 3, a significant reduction in the computational complexity. Okay, so now I can generalize this method for any value m. Generalized form, okay, for any value m. So the FIR part can be decomposed into log of 2 m different stages. Okay, by applying a power of 2 decomposition. So let I is the stage number, so I will be 0, 1, 2 up to log of 2 m minus 1. Okay, so this FIR part will be divided into this number of stages: stage 0, stage 1, stage 2 up to log of 2 minus m. So this is stage 0, 1, 2 up to log of 2m minus 1, like this, and the FIR part will remain as it is. Transfer function of stage 0 will be 1 plus Ez inverse. Stage 1 will be 1 plus e square z minus 2. Second stage will be 1 plus e raised to power 4 z raised to minus 4, likewise. So the power will increase by factor of 2. Okay, this is minus 1. So the power will increase by factor of 2. E raised to power 1 z raised to 1 minus 1, e raised to power 2 z raised to 1 minus 2, e raised to power 4 z raised to 1 minus 4, likewise. Okay, and the overall transfer function will be given by, okay, so this are cascaded, so we can multiply this. So multiplication from I equal to 0, starting from 0 to the last value, that is log of 2 m minus 1. Okay, this is 1 plus e raised to power 2 raised to power I z raised to power minus 2 raised to power I divided by the IIR part as it is, 1 minus e raised to power m z raised to power minus m, with poles at, so the poles will be located at z equal to a into e raised to power j 2 pi by m, e raised to power j into 2 into 2 pi by m, like this, up to e raised to power j m minus 1 into 2 pi by m. Okay, so I can write that poles are located at z is equal to a e raised to power j k k into 2 pi by m, and the value of k is 0, 1 up to m minus 1. So these are poles that can be calculated equating denominator equal to 0. Okay, and the zeros, so we have different stages and each stages will have different amount of zeros. So ith stage of decomposed FIR portion, that is a non-recursive part, will have 2 raised to power I zeros. Okay, so 0th stage will have 2 raised to power 0, that means 1 0. This will have 2, this will have 4. Okay, and the location is given by z is equal to a into e raised to power j 2n plus 1 divided by 2 raised to power I, this factor. Okay, for n equal to 0, 1 up to 2 raised to power I minus 1. Okay, so now in non-recursive part, so talking about adder and multiplier in non-recursive part, total adder will be log of 2m and multiplier will be also equal to log of 2m. Okay, so in decomposed non-recursive part, and in original filter, with m level of look ahead transformation, number of adders will be m minus 1, multiplier will be also equal to m minus 1. So here you can see that the area and also the computational complexity is significantly reduced.